Hello again, welcome to Basics of Finite Element Analysis Part 2. Today we are going to continue our discussion which we were having in the last class, and in last class we had developed element level equations for this bar problem which is shown here, and this was the governing differential equation, and for this equation for the element level we had arrived at these equations. So now what we will do in this class is that we will assemble these equations for the entire assembly, and when we do this assembly we will enforce some continuity conditions and equilibrium conditions for the assembly process. And once we have done the assembly level equations, then we will apply boundary conditions and finally solve the problem. Start doing the actual assembly, I wanted to discuss the methodology for enforcing for doing this assembly level operation. And to understand this, we have to understand what happens when two elements meet. So suppose this is eth element and this is E plus 1th element. The first element, the node number of eth element is 1 and 2. So the first node is 1 and the second node is 2. And likewise, the first node of eth, E plus 1th element is node number 1 and this is node number 2. Okay. In this picture, what I have shown is that there is a gap here, but in reality the gap is 0. The gap is 0 between these two elements because these two elements are physically touching each other. So for instance, if I have a bar, if I break it into 3 elements, this is element 1, this is element 2, this is element 3. So if I look at the node numbers for first element, this is 1 and 2, for second element this is 1 and 2, this is for third element this is 1 and 2. Okay. And the gap between this node and this node is 0. I can also assign global node numbers. So these blues, these are local node numbers. I can also assign global node numbers. So what will be the global node number? It will be 1, 2, 3 and 4. So these are global node numbers. So likewise, for eth element, my global node number for the first node will be E, then for this one it will be E plus 1 and for this one it will be E plus 2. Okay. So these are global node numbers. Now, if the gap is 0 and the two nodes are fused locally, then what does that mean? That the displacement U so the displacement for the eth element at second node is same as displacement of E plus 1th element at the first node, right? And this means this is equal to U E plus 1. So this is, these are local degrees of freedom and this is global DOF. So, once again the displacement of this node and the displacement of this node, the displacement of this node is signified by u2e, the displacement of this node is signified by u1e, and both of them are equal, and the value is same as the displacement of this global degree of freedom, which is E plus 1. Okay. So, this equality is known as continuity condition. That whenever there are two nodes which are merged, if they are not merged, if there is a crack, then they will not be same, but if they are fused together, if there is no crack, if there is no breakage, then they will have the same deflection or displacement or same temperature or whatever. Okay. So, this is the continuity condition. So, in context of our bar problem, so for the bar problem which we are doing, for the bar problem we have three elements, and for three elements we will have one continuity condition at this node and another continuity condition at this node. Okay. And what are those continuity conditions? So, first one is u, so this is the first element, 2 is equal to u 1, 2 is equal to u 2. And the second continuity condition is u 2 is equal to u 3 1 is equal to u 3. Once again, this is global and these are local DOFs. Okay. So, this is the first thing. When we are doing assembly, we have to make sure that when we assemble equations, these equalities are maintained. The second condition is, actually more precise would be force balance condition. So, what does it mean? So, again suppose I have two elements, this is eth element, this is global degree freedom 1, no local 1, local 2, this is E plus 1th element, local 1, local 2, and global degrees of freedoms are 1, 2 and 3. Then what does this mean? It means that if there is no external force at global DOF 2 or at global node 2, then net reaction force at this position will be 0. What does this mean? So, suppose I have a bar and this is 1, 2, this is E plus 1 and this is 1 and 2, and the global degrees of freedom are 1, 2, 3. Then when I break it at the element level, when I break it, what will happen? This is E plus 1th element, this is node 1 and node 2, and suppose I am pulling it like this, suppose I am pulling it like this, what will happen? There will be a reaction force which will, when I cut it, there I will see a force here. Similarly, so I will just create a small gap for, I will see a gap here, a force here, and on this element it will be acting in the other direction, and when I add these up, they should balance and they should vanish, right. So, when I am doing this assembly, the internal forces should add up to 0, but this will happen only if there is no external force at point 2. Suppose at external point 2, I am putting some at node 2, at this node, global node 2, I am putting some external force F. Suppose I am applying some external force F, then the sum of these two will be F. Because there is no external force, these two will add up as 0. Okay. So, this is important to understand. So, these are the two things we have to consider when we do the assembly process. So, with this we will develop the assembly equations. So, first we will write the 3 element equations. So, it is K11, K12, K21, K22, U1, U2 is equal to F1, F2 plus Q1, Q2. So, this is for the first element. So, the superscript is 1 everywhere. Okay. Then I write the equation for the second element, because our domain has been broken into 3 elements, right. So, we will have another set of equations for the second element. So, again it will be K11, K12, K121, K22, but here the superscript is going to be 2, indicating that these equations correspond to the second element, and then we have a third set of equations for the third element. Okay. So, the first thing so these are element level equations, and we have to compress them into assembly level equations, right. We have to assemble them together. So, when we are doing assembly level equations, the first thing we have to make sure is that we have to transform these local degrees of freedom into global. So, we know that U11 is equal to U1, U12 is equal to U21 is equal to U2, U31 is equal to U22 is equal to U3, right, and U32 is equal to U4. So, the first thing we do is we replace them, U1, U2, U2, U3, U3 and U4. So, once we have done this, we have enforced continuity. Okay. the next step is that we have to do the force balance. So, we have enforced continuity, now force balance. So, for force balance, here we have to add these forces at the interface together, right, which means I have to add these two equations and I have to add these two equations. Together. Why? Because when I add these two equations together, Q12 gets added with Q21, these two add, and if there is no external force, then their sum will be, when I add these two equations, this is the internal force, right. So, this is the internal force representing this thing, and this is the internal force representing this thing, and if there is no external force at this point, then these two will add up to be 0. So, that is what we do. So, ultimately how many equations will end up with? See, right now we have 1, 2, 3, 4, 5, 6 equations. How many degrees of freedom we have right now? 1, 2, 3 and 4, right. We have 4 degrees of freedom. So, we have to reduce 2 equations. These 2 are being reduced by adding these 2 equations together, right. So, when I do the assembly, my assembly, it looks something like this. So, this is the first equation, K11 times U1 plus K12 times U2, and then in the first equation there is no U3 and U4. So, the coefficients on the K matrix are 0. Okay. Now, let us look at the second equation. In second, so we have to add second and third equation together. We have to add second and third equation together. So, when we add them, this is what we get. Okay. So, this is the second equation, K21 for the first element times U1 plus K22 1 plus K112 times U2 plus K122 times U3, and there is no U4 in these two equations, right. So, it is 0 here. This is the second equation, and then the third equation is 0. In the third equation, there is no U1. So, the K matrix element is 0 for there is no U1. So, this element is 0, and then here we get K21 2, and this is K222 plus K113, and this is K123, right. So, this is the third equation, and the fourth equation is 0, 0, K213, K223. So, this is the left side of the equations. The right side is F11, F21 plus F22, excuse me, 1, and then I have F22 plus F13, and then I have F23. So, this is the matrix related to external forces, and then I have Q1 1 and then Q2 1 plus Q2 1, and then this is Q1 3 plus Q2 2, and this is Q2 3, right. And now I enforce the force balance thing. So, this is the sum of these two is 0 and the sum of these two is also 0. Okay. So, these two things are 0. They will not be 0 if there is an external force at that point which is being applied, but if there is no external force, then these will be 0. Okay. So, now this vector is known. Why? Because we know Q is known and HE is also known, right. So, this vector is known. All the elements in this matrix we have calculated. So, this is also known. This is not known. So, this is unknown, and this is also unknown at this stage, right. So, U1, U2, U3, U4 they are unknown, and also this Q11 and Q23 are unknown. Everything is known, but we have 4 equations and 6 unknowns. 4 equations and 6. So, to solve these equations we need 2 extra conditions. Okay, we need 2 extra conditions. So, we need 2 extra conditions. These come from boundary conditions. Okay. So, you can have a bar, suppose this bar is like this and I am pulling it like this. So, this is node 1, this is node 2, node 3, node 4. Then what are in this condition, in case what are the 2 extra conditions? That at node 1 U1 is 0, right, and at node 4 is U4 known. The first condition is that at node 1 U1 is 0, the second condition is that at node 4 we do not know U4, but we know force. So, Q23 is equal to F. Okay. So, this is one, but there could be other boundaries. So, once we have found these two, applied these 2 conditions, then we will have 4 knowns and 4 unknowns and 4 equations. Another situation could be you have a bar and I am applying force here and I am applying force here. In this case, what is the case? U1, U2, U3, U4 are unknown, but force at node 1 and force at node 2 are known. So, Q11 is equal to F and Q23 is equal to F, right. So, likewise we have to get 2 extra conditions. Once we, so those we get from boundary conditions. Once we get those, then I have an equal number of unknowns and equations and I can solve those, and then I get the solution for the overall system. So, this is a very brief overview of whatever we did in the last course, and going forward we will start looking at different dimensions of this course with newer topics. Thank you very much and look forward to seeing you in the next week. Bye.